Okay, in this problem, we're going to use our newfound calculate and carry back method of analyzing circuit charts to analyze a more complex circuit. So this circuit has a battery, and it has 1, 2, 3, 4, 5 resistors that could stand for a variety of things that are plugged in my house. And I have a bunch of questions down here that people are asking me about this circuit. For example, what is the voltage drop across the 3.2 ohm resistor? That means, like, how many sticks of dynamite is it going to cost me to cross this 3.2 resistor? I don't know. And there's no way to find that answer without using a circuit chart. Determine the current flowing from the battery. Such a simple question. There's no way to get that answer without using the circuit chart. So bear with me. This method is, it's a simple method, but it's very complicated on your paper, and it's going to look really, really messy. So the first suggestion that I have is that you use different colors. And I always use red for showing equivalent resistors and to kind of show my work in terms of what I'm combining. And also I'm going to use the process of drawing my subcircuits down over here and drawing my circuit chart in this space. So try to do your work on your paper at the same place I'm doing my work, because I'll make sure that it fits on our paper. Okay, so I always start by trying to understand the circuit a little bit better by pretending that I'm the marching electron or the marching ant and seeing what would happen and where my choices are, so I can try to get a sense of who is in series and who is in parallel. So here we go. We are the marching electrons, and we're coming out of the positive side of the battery. So march, 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 march. We all go through the 4.5 together. We all go through the 1 together. That tells me that the 4.5 and the 1 are in series. And then we get over here and we hit a junction. And some of the marching electrons might choose to go this way through the 7.1 and through the 5.8. And since they would all have to go through both of those, that tells me that the 7.1 and the 5.8 are in series. But some of the marching electrons might have turned the corner and gone through the 3.2. So that tells me that the 3.2 is in parallel with this other line over here. The other day when we were learning about equivalent resistances, I told you to kind of like analyze mini circuits first and to kind of combine those resistors first. And the second rule that I told you is if you don't have any mini circuits, then start as far away from the battery as possible. And that's the rule that I'm going to apply right now. So since I don't really know what to do, I know these guys are in series, I know these guys are in series, and that I'm going to start as far away from the battery as possible. So I'm going to combine the 7.1 and the 5.8. Let's talk about these two a little bit more slowly. When you first look at the picture, you might think they look parallel to each other because you see these two parallel lines. But that's not how you tell if something's in parallel. If the electrons chose to go through the 7.1, would they have a choice about going through the 5.8? No, they're forced through the 5.8. That's how I know that these two have to be in series. So that's what I'm going to choose to combine. So I'm going to draw a picture, and the picture that I draw, the little sub-circuit that I draw, is going to be like a smaller mini version of the big circuit. And I'm going to put in my original 4.5 ohm resistor, my 1 ohm resistor. I'll put my battery down here, 12 volts. I'm going to put the 3.2 ohm resistor. But I'm going to, instead of having a 7.1 and a 5.8, I'm going to combine them, pretend that I'm going to go to Radio Shack, and since they're in series, I'm going to add them together, and that adds up to 12.9. That means that I could throw in an REQ of 12.9 ohms, and the circuit would function the same way. All right, but notice I did two things that are going to help me later. Number one, I circled what I was combining so I know where I got the 12.9 answer from, and I made it a different color and labeled it in REQ. All right, so we want to keep the original R values separate from REQ values. All right, the next thing is I want to point out that we are doing the calculate and carry back method, which means in between every picture, we're going to have some calculations to happen. So I need to create some space for those calculations to happen. So I'm going to go down here a little bit lower. All right, the next thing I'm going to do is I'm going to combine these two. Why am I picking these two? Well, two reasons. Number one, if the electrons came out of the battery and they went over here and they hit this junction, I could see that some could go this way through the 12.9 and some could turn through the 3.2. That tells me that these two things are in parallel, so they can be combined. And secondly, I'm starting as far away from the battery as possible, and I'm collapsing and working myself towards the battery. So I'm going to collapse the circuit, leave yourself space to calculate. So we're going to go down here. And I'm going to put back in the battery. That's 12 volts. We're going to put back in the 4.5, the 1. But I am going to collapse those that are in parallel and replace them with just a single REQ. I just have to figure out what that value is. And so that value is going to be 1 divided by 3.2. Here, let me do it this way. 1 divided by 3.2 plus parenthesis 1 divided by 12.9. And then I have to do 1 divided by the answer to flip it back over. And I get 2.56. 2.56. So this is going to be 2.56 ohms. So if I put a 2.56 ohm resistor in, it would kind of like function the same way. All right, am I done? No, I'm not done. You're not done until you have one battery and one resistor. All right, let's talk about those electrons again. If the electrons came out of the battery, they would go through the 4.5, they'd go through the 1, they'd go through the 2.56. They would like have to go through all of them, and they would have no choices, which tells me they're all in series. So I should have just circled them in red, and I just picked up a green pen, so that was bad. All right, so leave rooms to do some calculations. Let's collapse our circuit a little bit more. So let's put the 12 volts in here. And we are going to replace all three of those resistors in series with an REQ of, let's add them up. So we have 4.5 plus 1 is 5.5 plus 2.56. That adds up to 8.06. Okay, so I'm done because I have one battery and one resistor. I'm done finding the equivalent resistance. I'm far from done with the problem. All right, what do I do next? I am going to calculate, and I'm going to start by, when I say the word calculate, we mean apply Ohm's law, VIR. And I know that my battery is 12 volts. I know that the REQ is 8.06. So I can calculate the current. What this current is it's the current coming from the battery. So I'm using this picture here. Let me circle. I'm using this picture to calculate. So I'm going to do 12 divided by 8.06, and I get 1.49 amps. 1.49 amps. We'll come back and use that in a second. All right, the next thing I'm going to do is I am then going to do PIV, P equals IV. So I'm going to take that current of 1.49, and my battery is 12 volts. And I'm going to calculate the power. This is the power. Since this REQ encompasses all of these guys, it's the power used by the whole circuit if I had everybody plugged in at the same time. And that turns out to be 17.88 watts. Okay, so before we talk about what to do with these answers, let's prepare our circuit chart because we're going to need it here pretty soon. All right, so our circuit chart is, I always remember the headings by its VIR backwards. So R, I, and V. Then we'll throw a P on there. And how many rows do I need in my chart is how many resistors that I have. So 1, 2, 3, 4, 5. I need 5 rows. So there's 1, 2, 3, 4, 5. So let's close these up a little bit. All right, so let's put in the R values. It doesn't matter what order that you do that. So I'm just going to kind of look at my picture and put them in order of the picture. 4.5, I see a 1, I see a 3.2, a 7.1, and a 5.8. All right, and we also noticed over here that I'm going to put that extra box down here, that we learned that if we plugged everybody in together, that we would draw 17.88 watts of power. So when I'm all done, if I add up all of the power values and they're 17.88, I can feel pretty confident in my answers. And by the way, by the time we do all of the math and all the work on our paper here, there could be some round off error here. Sometimes some rather significant round off error. So don't get too bent out of shape if there's not a perfect match there. Okay, so that's why we do PIV. PIV is just a way to check my answer. The calculate carry back method is all about Veer. Veer is Ohm's law. So this is how you use the calculate carry back method in a more sophisticated picture or circuit such as this one. So your last picture, you use the last picture to calculate. And when I say the word calculate, I mean use Ohm's law and get your answer, 1.49 amps, and take your answer and carry it back to the picture before. This is why if you skimp on drawing your pictures, when you're trying to find the equivalent resistance, you'll be carrying it back to the wrong picture, and then it won't give you the answers that you need. So you have to draw the pictures correctly so that when you carry back, you keep bopping back to the correct circuit. All right, so what I do then is I talk to myself when I carry back. So bear with me as I talk to myself here. All right, so what we learned here from this last picture was that the current coming out of the battery was 1.49 amps. So I'm going to carry that back and I'm going to put that in the picture. We just learned that the current coming out of the battery was 1.49 amps. What does that mean, current coming out of the battery? First of all, it tells you how fast the electrons are traveling. They're traveling 1.49 coulombs per second. Okay, so here they go. 1.49 amps goes through the 4.5. I can write that in my chart. The current going through the 4.5 is 1.49. We just figured that out. So current going through here is 1.49. By the way, you might say, well, how many sticks of dynamite would that have costed me? V equals I times R. We can calculate that right there. I just don't want to slow down the story by talking about the sticks of dynamite right now. So we'll go back and figure that part out later. All right, so here we go. 1.49 went through the 4.5, and 1.49 current went through the 1. I'm going to write that in. 1.49 current went through the 1. And then I come over here, and 1.49 current went through the REQ. But I can't write that in the chart because there's no 2.56 in the chart, because there really is no resistor 2.56. It's not one of these. It's just an REQ. It's just a concept. It's just an idea. So every time you hit an REQ, that's where you calculate. And when you calculate, you're going to write down Veer. You're going to write down Ohm's law. And you're going to calculate whatever you don't have. So let's see what we were just doing. We were just marching with a current of 1.49, and we encountered a REQ of 2.56. We encountered an R value of 2.56. So I guess we're going to learn the voltage, we're going to learn like how many sticks of dynamite it would take to go through this. So that's going to be 1.49 times 2.56, 3.81 volts. That's going to cost me 3.81 volts, sticks of dynamite, to get through that. I learned something. I can't write it in the chart because the REQ doesn't exist. So I calculated and I now carry it back to the picture before me. But when I say carry it back to the picture before you, we can even be more specific. You're really going to carry it back to whoever or whatever made up that REQ. That's why I circled it. I circled this red REQ is made up of those two things. All right, we got to pause here for a minute. We have to learn something new. So I want to show you that you already know that in series, you add up the REQs. In parallel, you 1 over the R values. But here's something else we're going to learn. When you have resistors that are in parallel, the voltage is the same. The voltage is the same. So let's apply that right here. So this REQ was 2.56, and it was made up of this 3.2 and this REQ. And voltages in parallel lines is the same. That means it would cost me 3.81 sticks of dynamite volts to go through that REQ. And it's also going to cost these electrons 3.81 volts for sticks of dynamite to go through that 3.2 there. But you know what? This is a real resistor. That's in my charts right there, 3.2. And it's going to cost me 3.81 volts, sticks of dynamite, to go through that. So if it's a real resistor, I can write it in the chart. All right, but this one's not a real resistor. And when it's not a real resistor, that's when you have to calculate. That means apply Ohm's law. So I'm going to go up here and I'm going to apply Ohm's law, and I'm going to calculate whatever I don't have. Well, what did I just learn? My voltage was 3.81. It's going to take 3.81 sticks of dynamite to go through this 12.9 ohm REQ. So it looks like I could learn the current. I could learn the current through this path. So that's going to be 3.81 divided by 12.9, and that is 0.3, maybe 0.3. 0.3. I wonder if I rounded off too much. I'm going to go for it. 0.3 amps. All right, so I calculated, and I'm going to carry it back to whoever made up this REQ. Who made up the REQ? That would be whoever I circled. So you know what I just learned? I just learned right here how fast the electrons would be going through this path. I just learned the current through the 7.1 and the 5.8. The current is 0.3. So I'm going to write that down. So then I'm going to talk to myself. So the current going through the 7.1 would be 0.3. I could write that down, 0.3. And then the marching electrons would keep on going down, and then it would still be 0.3 through the 5.8. 0.3. All right, I'm done talking to myself, and now I just kind of like have a big mess on my paper. And so we used this calculate carry back method to just learn little tidbits along the way, and we collected our tidbits in the circuit chart. But now let's focus on the circuit chart. If you have two values in a row, you can calculate the rest of the row because we know that V equals IR, and we know that P equals IV. So I'm going to use that information to fill in the rest of the chart. So right now I'm just going to number crunch, then we'll try to put some meaning to it. So I have, so to get the sticks of dynamite or the voltage through the 4.5, I'm just going to do V equals IR. So 4.5 times 1.49. That's going to be 6.71. And then P equals IV. Since I already have the V on my screen, I'll multiply times 1.49. And that is going to be 9.99. All right, so this would be a 1.49. 1.49 times 1.49. That's going to be 2.22. All right, so this is V divided by R. 3.81 divided by 3.2 would give me a current of 1.19 times 3.81 to get my power value. That'd be 4.54. 7.1 times 0.3 voltage drop of 2.13 volts times 0.3 will give me a power of 0.6. I'll round this off to 0.64. And then 5.8 times 0.3 will be 1.74 times 0.3, 0.52. All right, moment of truth. We are now going to add up the powers, 9.99 plus 2.22, and we're going to hope that they are close to what they're supposed to be. 17.91. That's close enough to 17.88. All right, so I feel pretty confident with those numbers. All right, so let's now answer the questions on the bottom and then come back up to the top to try to create a little bit more meaning here. All right, calculate the equivalent resistance of the circuit. We did that right here. 8.06. So the REQ for the whole circuit is 8.06 ohms. Determine the current flowing from the battery. We did that down here. It was 1.49 and we carried it back. 1.49 amps came out of the battery. So 1.49 amps. What is the power dissipated by the external circuit? Dissipated means like lost or used up or spent. So if you had all of these resistors plugged in, how much power are you using? That's the 17.88, or if we added it up and got 17.91, either way. So 17.88 watts. All right, now what I want you to see is that these answers here are all going to be in the circuit chart. So what is the current that passes through the 5.8 ohm resistor? So you find the 5.8 ohm resistor. What's the current? 0.3. 0.3 amps goes through there. By the way, 0.3 is a small number, like the electrons are not flowing very quickly through the 5.8 resistor. They're going kind of slow through that one. What is the power dissipated or spent by the 1 ohm resistor? Here's the 1 ohm resistor. What's the power? So if you plugged in just that one, you're drawing 2.22 watts of power. So 2.22 watts. What is the voltage drop across the 3.2? So that's kind of fancy language, voltage drop. It kind of means like how many sticks of dynamite you had here, and then you had to spend some sticks of dynamite to get down here. Like that means your voltage dropped. So it really means what is the voltage? How many sticks of dynamite do you have to spend to cross the 3.2? How many sticks of dynamite do I have to spend to cross the 3.2? 3.81 sticks of dynamite or volts to go through there. That's the voltage drop. At what rate, or what is the rate at which energy is lost by the 7.1? We are going to spend energy when we plug things in. When you spend energy, that's just a fancy word for power, because the rate energy is lost, energy over time, that's power. So what is the power lost by the 7.1? That's 0.64 volts. 0.64 volts. All right, this one, I'm just going to not even talk about it. We're just going to cross that one out. All right, and we have not talked about I or J yet. So, briefly, I'll give you a quick introduction of those. So, it says, suppose you wanted to measure the current passing through the 5.8. We wanted to measure the current. Draw the proper meter in an appropriate location. So, if you want to measure current, you use something called an ammeter. An ammeter. And the symbol in a circuit for an ammeter is a circle with an A. So it just means that you put this meter in the circuit. And if we want to measure the current passing through the 5.8, which by the way, we know the answer is 0.3, but the current passing through this whole line is the same. It's 0.3, 0.3, 0.3, 0.3, 0.3, 0.3. So I could put that meter anywhere that I want. So I'll put it right there. And that meter probably has a little prong on the top that you'd connect the wire to, and another little prong here that you connect the wire to, and it would give you a digital readout of 0.3. All right, suppose you wanted to measure the voltage drop across the 3.2. Like, how many sticks of dynamite is it going to cost me to go through the 3.2? Well, we know the answer is 3.81, but what if I wanted to have a meter to measure that? So if you want to measure voltage or voltage drop, you use what's called a voltmeter. A voltmeter. And the symbol for a voltmeter is a V. But voltmeters have like this little wire that comes off of them. And voltmeters have to be connected in parallel. So if I want to, it's like I have to take one of the little wires and put it before the resistor. Then I got to take the other little wire and I got to put it after the resistor so that I could see how many sticks of dynamite I had here and then how many that I had here. And then I could see how many I would have spent to go through the 3.2. So ammeters end up being like just right in line, which means ammeters are connected in series, and voltmeters end up connected in parallel with your resistor there. All right, we have one last thing to talk about. And the one last thing that we have to talk about is the meaning behind this circuit now. So now I want you to look at the numbers as we have all of our answers and we talk through the circuit up here. So we learned that the current coming out of the battery was 1.49. So I'm going to write down I equals 1.49. So all the electrons are all together marching along. 1.49 goes to the 4.5. That makes sense. All the electrons go through the 1. 1.49 goes through the 1. That made sense. And now there's a choice. Some of the electrons are going to turn and some are going to go straight. How many are going to go straight? So what went through the 7.1 and the 5.8? 0.3 went straight, 0.3. So if we had 1.49 over here and 0.3 went straight, then how many would have had to have turned? So 1.49 minus 0.3 is going to be 1.19. That would mean like 1.19 would go through the 3.2. And look at that. 1.19 went to the 3.2. And then they all met up down here. And if there was a resistor over here, it would have been back to a 1.49 because they would have all been together. All right. Then the last little teeny piece is how come only 0.3 went straight, and how come so many of them chose to turn? I want you to picture electrons being super, super lazy. If I was the electrons, like this is why I would not want to go straight. Look at the mountains that you would have to encounter. Look at the resistance that you would have to encounter. You're going to encounter a mountain of 7.1. You're going to encounter a mountain of 5.8. And this is the phrase that in physics is called the electrons will take the path of least resistance. Wouldn't it be easier to, instead of going over a mountain of 7.1 and then having to go through another mountain of 5.8, just to go over a baby mountain of 3.2. So honestly, most of the electrons, they all wanted to turn because that's the path of least resistance, but they didn't all fit. And some of them got forced to go this way. And that's why the current number is so small, because they're slowed down by this big mountain. And then they're coming over here and they're slowed down by this big mountain. And the ones over here are faster. They went 1.19 amps all the way through here. And then they're all back to the battery again. So the story should make sense when you go back and you take your final answers and you walk them around the chart. Things should make sense when you look at the alternative paths that the electrons could have taken. But there's no way that I could have got those numbers without going through this process. So that's what we're trying to learn, is what these words mean, how the process goes, but then put the meaning back into the story. So I know this was a very, very long problem, and some of your homework problems are just as long, which is why I'm offering to do them with you in optional Zooms later this week. Okay, so go through this a couple of times until you feel better with it, and be prepared to ask questions on the Zoom if necessary.